Hi everyone. Today we're going to be completing our notes on section 6.2. These are our first notes in our new topic 6 on exponential functions. I want to start with the warm-up using 2 sheets of paper. Let's go ahead and fold one of them accordion style for 5 folds. And after each fold, we're going to count the number of rectangular sections. And then we're going to record the number in the table here. For the second sheet of paper, we're going to fold it in half 5 times. And we're also going to count the number of rectangular sections. Okay, so starting for that first one, if you need to pause the video to grab 2 sheets of paper, go ahead and pause right now. Okay, so for style 1, accordion style, before folding it at all, we have a single rectangular sheet of paper. After we fold it once, we then have 2 rectangular sections. If I fold it again, then we have 3 rectangular sections. And if I fold it again, we have 4. And you can start to see that pattern. After 4 folds, we have 5 rectangular sections, and after 5 folds, we have 6 rectangular sections. For the other style, where we fold it in half each time, well, again, before any folds, it's 1 rectangular sheet of paper, and then after we fold it in half, we have 2 rectangular sections. Folding it in half again, and then unfolding it, we count. There are 4 total rectangular sections. Folding it back up and folding it in half once more, we get 8 rectangular sections, then 16, and then 32 rectangular sections. Okay, so we notice a difference in the number of rectangular sections depending on how we fold the sheet of paper. For every accordion style fold, the number of sections increases by 1. This would be represented using a linear function. We see that for every increase in x, we have a linear increase in y. For every half fold, or in style number 2, the number of sections multiplies by 2. Another way you can think of this is the number of section doubles. This would be represented using an exponential function. Okay. So example 1, given the two functions f of x equals 2x and g of x equals 2 to the power of x, complete the table below. Okay, and then we're going to plot both of these on the same grid to the right. So I'm going to label f of x, I'm going to graph that in red, and then g of x, I'm going to graph in blue. Okay, so we'll start with the linear function f of x. If I plug in values like -3 into f of x, so f of -3, we multiply 2 by -3. This evaluates to -6. Multiplying -2 times 2, we get -4, -2, 0, 2, 4, and 6. Okay, so these are the function values for the x values, the inputs of the table. If we were to go ahead and plot this on the graph, this would be a linear function with a y-intercept of 0 and then a slope of 2. So we can plot that y-intercept of 0, and then using our slope of 2, up 2 to the right 1, up 2 to the right 1, you can plot the points on this line. And if you have a straight edge, you can use that to sketch your line. Don't forget those arrowheads. This extends infinitely in both directions. Now for the function g of x, this is going to look a little bit different. Remember, this is raising to the power of 2. Let's start with x equals 1. What is 2 to the power of 1? Well, 2 to the power of 1 just means 2 by itself, multiplied by itself 1 time, or just 2. 2 to the power of 2, so moving down in the table, would be the same as 2 squared, or 2 times itself 2 times, which is 2 times 2, or 4. G of 3 is 2 to the power 3, or 2 times 2 times 2, which is 8. And so we can see as we move down in the table, our function outputs are being multiplied by 2. So times 2, times 2. So we would expect that as we move in the opposite direction, our function outputs would be following that inverse operation. So rather than going down the table and multiplying by 2, if we go up the table, we would expect the function outputs to be divided by 2. Therefore, g of 0 is equal to 1. And g of -1 would again be divided by 2, so 1 over 2, or 1/2. G of -2, dividing 1/2 by 2, we would get 1/4. And then dividing 1/4 by 2, we would get 1/8. So g of -3 is equal to 1/8. Okay, So these are the function outputs for g of x. If we were to plot these values on the grid to the right, well, we have a y-intercept of 0, 1. We have 1, 2, which is the point they have in common. We have 2, 4, another point they have in common. We have 3, 8. And then in the negative x, we have negative 1, 1/2, negative 2, 1/4, and negative 3, 1/8. If you were to continue, you would have like negative 4, 1/16, negative 5, 1/32, and so on. So if we sketch this graph, we have a graph that looks like this. So be very careful when you're drawing your graph. This curves upward. And so what we have is a graph that looks like this. Now, I'm going to actually correct something on my graph. I'm going to try really hard not to cross that x-axis. And the reason why is as we move out in those negative quantities, like I said, negative 5, 1/32, negative 6, 1/64, as we move out to the left, as x gets greater and greater in the negative direction, these quantities, these function outputs are getting smaller and smaller and smaller and smaller. They get extremely tiny. Like if we were to plug this into a calculator and get a decimal approximation, it would be like 0.00001, something like that. However, no matter how far out to the left we go, these functions will never actually reach 0. Okay, so the function approaches 0 but never reaches. So we don't actually want to cross that x-axis at all, because remember that x-axis is where y equals 0. We want to get really close but without crossing. Okay, so part A, which column is growing faster? Well, looking at the function outputs, I notice that g of x is growing faster. The pattern of growth for f of x is equal to 2 of x is an added constant value of 2, which means that the function is linear because we are adding the same value each time. So if we look at the table, all of these red values increase by 2. We add 2. However, for g of x, we have a constant multiplier or a constant ratio of 2, which tells us that this function is exponential. Okay, so let's try example 2. Here we have p of x equals 1/2 x and q of x equals 1/2 to the power of x. As same as before, we'll fill out the table of values. So starting with p of x, I'm going to graph this one in red. So p of x is 1/2 x. If I were to plug in negative 3, we would have 1/2 times negative 3, which is equal to negative 3/2. If I plug in negative 2, 1/2 times negative 2 is equal to negative 1. If I plug in negative 1, that's going to give us negative 1/2. If I plug in 0, we get 0. 1/2 times 1 is 1/2. 1/2 times 2 is 1. And 1/2 times 3 is 3/2. For q of x, I'll go ahead and graph this in blue. Oh, actually, let's go ahead and graph p of x first. So here we have a y-intercept of 0 and a slope of 1/2. So we can go up 1 and to the right 2, plotting our points from our table of values. As always, use a straight edge, a ruler, calculator case, ID, things like that. Again, use a straight edge, draw those arrowheads at the end of your graph. This goes on infinitely in both directions. Okay, so now let's go ahead and graph q of x in blue. So let's start with x equals 1. If I do 1/2 to the power 1, that's 1/2 times itself one time. 1/2 to the second power, 1/2 squared, is equal to 1/2 times 1/2, which we know is equal to 1/4. Multiplying by itself 3 times, or q of 3, we get 1/2 times 1/2 times 1/2 gives us 1/8. So it follows that as we move down the table, we are multiplying our function outputs by 1/2. Therefore, as we are moving up the table, we would expect to follow the inverse operation, or multiplying by 2, or dividing by 1/2. So then q of 0 is equal to 1. And then q of negative 1, we have 1/2 to the negative first power, would be equal to 2. 1/2 to the negative second power would be equal to 4. And finally, to the negative third power would be equal to 8. Okay, so as we move up the table, our function outputs are divided by 1/2 or multiplied by 2. So let's go ahead and plot these points. We have a y-intercept of 1. We have 1, 1/2. We have 2 1/4. We have 3 1/8. We also have negative 1 2, negative 2 4, and negative 3 8. And so we have this function here that as we read from left to right, this would be decreasing. And just like before, as we increase x, as we move out to the right, we would expect these quantities to go from 1/2, 1/4, 1/8, 1/16, 1/32, and so on. They would get smaller and smaller and smaller. But just like before, as we increase x, this function is never going to reach 0. There's never going to be a value x that we can plug into this function that's going to equal 0. Therefore, our function will never cross the x-axis. All right, so part A, what is the constant value that is being added in p of x? So what are we adding each time? Well, in this case, we are adding 1/2. That's our rate of change, our slope in the linear function. Okay. For part B, in order to find the constant ratios of exponential functions, we can find the ratio between any two consecutive terms. Okay. Therefore, if I look at g of x, so on page 1, the ratio that we're finding here is what we're multiplying by every single time that we move down each row, assuming that x is increasing by 1. So for every successive x, this is the ratio that we're multiplying by. So in g of x, we're multiplying by 2. In q of x, again, for every successive increase in x, what are we multiplying q of x by? And the answer is 1/2. So one thing I notice is that in g of x, because our constant ratio is greater than 1, let's see what happens in our graph. G of x is increasing. We would call this exponential growth. In q of x, because we have a constant ratio that's less than 1, 1/2 is less than 1, but still positive, well, let's see what happens with the graph. It's decreasing as we're moving to the right. So we have an exponential decay factor. The line that the graph of an exponential function approaches but does not touch is called an asymptote. The equation of the asymptote for q of x is y equals 0. So again, that function approaches the y value of 0 but never actually reaches it. In fact, this is the same equation for the asymptote in g of x. The function approaches 0 as we move out in the negative direction. The initial amount, or the y-intercept, is also a key feature of the graph. So let's look at p of x and q of x, and let's see what are the y-intercepts. So here, the y-intercept of the linear function p of x is equal to 0. In q of x, the y-intercept is 1. So as ordered pairs, p of x, we have 0, 0, and q of x, 0, 1. Now remember that domain is the set of all x values, all of the inputs that we can plug into the function. And then the range is the set of all the y values, all of the outputs of the function. Therefore, the domain for p of x, our linear function, is all real numbers. You can plug in any value into a linear function. So we're going to write this from negative infinity to infinity. You can plug in any number. This also means like all real numbers. The range, we can also say, is all real numbers because there's no function output that the function doesn't hit. So if we look at the graph, we're going to hit all y values. If we extend this infinitely in both directions, we're going to hit every single y value. Now for q of x, it's a different story. If we look at the domain, are there any x values that we can't plug in? Well, no, we can plug in any x values. So the domain is still the same. We have from negative infinity to infinity. But the range is a little bit different. Are there any y values that we can't hit or any y values that we never reach? Well, yeah, we discussed that the function is never going to reach y equals 0. Likewise, the function will never go past 0. It will never be less than 0. It's only going to be those positive values. So we would denote this as from 0 to infinity. Now, we don't want to include 0 because the function does not hit 0. So we denote this using a parenthesis. If we wanted to say that the function does hit 0, then we would include it by using a square bracket rather than a parenthesis. All right, let's go ahead and flip the page. So here is our general form for exponential functions. F of x is equal to a times b to the x. Now notice a few things here. A is the initial amount. it is also representing our y-intercept. B is the constant ratio. It's our growth or decay factor. It's telling us how much is the function increasing or decreasing for every successive x. So if we were to look at g of x and q of x, so going back to these, like let's look at q of x, this would be exponential decay, which we discussed, where the decay factor is 1/2. That means for every one to the right, every movement x1 to the right, the function is going to be decreasing by a factor of 1/2. So we would go from 8 to 4 to 2 to 1 to 1/2 and so on. Okay. For g of x, our growth factor is our exponential base here, 2. So this is saying that for every successive x, the function doubles. It's being multiplied by 2. That's our constant ratio. Okay. A couple things to note. A can't be 0, because if it's 0, then this whole quantity becomes 0. And b has to be positive. We can't have a negative base. And then also b can't be 1, because if b is 1, well then for any value x, that exponential factor is going to be 1. Okay? So identifying the key features of each exponential function. Here we have, this would say 4 times 3 to the power x. The constant ratio is going to be that b value. That's going to be inside the parentheses, that exponential base. It's going to be equal to 3. Because 3 is greater than 1, we know that this is exponential growth. The y-intercept is that initial value, so as an ordered pair, we have 0, 4. The asymptote is the y value that the function approaches but never reaches. We know this to be y equals 0. And domain for all exponential functions is always going to be all real numbers. So we have from negative infinity to infinity. The range is going to be everything above the asymptote, or from 0 to infinity. And again, we don't want to include 0 because it's the asymptote. It never will hit that value. So a quick sketch of this graph. Here we have, let's see, we have a y-intercept of 4. So 1, 2, 3, 4. That would be the y value. And then it's exponential growth. So as we move to the right, the function is tripling. And then we're approaching that asymptote y equals 0. Sometimes I like to draw my asymptotes as dotted lines because it affects the graph, but it's not part of the function. Okay, so letter B. Here we have f of x. The constant ratio is that exponential base. Here we have 1/3. Because 1/3 is less than 1, we know that this function is exponential decay. The y-intercept is that initial value, so as an ordered pair, 5, 0, 5. Asymptote is the y value that the function approaches but never reaches, y equals 0. And that's the equation for the horizontal line. Domain is going to be, again, from negative infinity to infinity. That's true for all exponential functions. And then finally, range. This is going to be everything above that asymptote, or 0 to infinity. So a quick sketch. We know that this is exponential decay with the y-intercept of 5. So if I were to graph this, 1, 2, 3, 4, 5, here's our y-intercept. And then it's going to be exponential decay. And I'm going to approach the x-axis here. I'll go ahead and draw on that asymptote too. All right. Example 4, identify the key features of the exponential function. So given representation A, here we have f of x. This is a table of values. The constant ratio is as we increase 1 in the x direction, what happens to our f of x? Well, we're multiplying by some number. In this case, to get from 800 to 400, we multiply by 1/2. And to get from 400 to 200, we multiply by 1/2. One way that we can represent this is take some x value and put it over the x value right before it. So 400 over 800 reduces to 1/2. That's another way you can do that. Okay, so the constant ratio is 1/2. So we know because that's less than 1, we have exponential decay. The y-intercept would be for where x equals 0, right? So as an ordered pair, we'd have 0 and then some number. Well, this table of values doesn't have x equals 0. So we have to think, what's going to be f of 0? Well, if we're multiplying by 1/2 as we move to the right in the table, I would expect to be dividing by 1/2 as we move to the left, or multiplying by 2. Therefore, the y-intercept is 0, 1,600. So then the equation, now that we know our y-intercept and we know our decay factor, we can write our equation, f of x is equal to our initial value, 1,600, times our growth factor, 1/2, and then to the power x. For part B, here we have another table of values, also represented as f of x. Our constant ratio, what's happening each time? Well, we're doubling this each time. 5 to 10, we multiply by 2. 10 to 20, we multiply by 2. 20 to 40, multiply by 2. And 40 to 80, we multiply by 2. Using that other trick, we could take successive x's. Let's go ahead and take, say, 40 over 20, and we can find that ratio to find our constant ratio. So 40 over 20, again, reduces to positive 2. So because 2 is greater than 1, we have exponential growth. Our y-intercept is where x equals 0. The ordered pair of coordinates for our y-intercept is 0, 5. So our equation, f of x, is equal to 5 times 2 to the power x. All right, go ahead and flip the page. Example 5. Here we want to identify the key features of each of these graphs. So the y-intercept in graph A, where does it cross the y-axis? Well, I know that each increment is 1, and it's just above 3, so therefore the y-intercept is 4. And I'm going to find a few other points on the graph. I notice we have 1, 2, we have 2, 1, and that's all of the points that cross the grid lines. So I notice that, well, if I know that it's going to be in the form y equals a times b to the x, well, let's go ahead and use the point. Let's use 1, 2. Okay. If I plug in the values 1, 2, x comma y into this general form here, and then also a right here for our y-intercept, we can use that to solve for b. Okay. So if we plug in 2 for y, we plug in 4 for a, and then we plug in 1 for x, then we can get 2 is equal to 4. Well, b to the 1 is just b, so 4b. And then dividing both sides by 4, we get b is equal to 2/4 or 1/2. So therefore, our constant ratio is 1/2. So we could write the equation from this graph. We know that this is exponential decay. 1/2 is less than 1. The equation, y equals our initial value, which was 4, and then times 1/2 to the x. The asymptote, again, is y equals 0. Domain is all real numbers from negative infinity to infinity. That's the set of inputs. And the outputs, the range, we have everything above 0. So from 0 to infinity. Okay, so for part B, here we have this function. I notice that the y-intercept, where it crosses the y-axis, is 0, 2. And then choosing some other points, I see that it crosses again at like 1, 6. And then that's right about it. So putting it into the general form, again, y equals a times b to the power x. Let's use the point. We're going to use the point 1, 6. Okay, so plugging it in, x comma y, we get 6 is equal to a, which is 2, times b to the power x, which is 1. Well, again, b to the power 1 is just b, so we get 6 is equal to 2 times b, 2b. Dividing both sides by 2, we get b is equal to 3. So our constant ratio is 3. Because this is greater than 1, we know that we have exponential growth. Okay, so the equation here, we have y is equal to a times b to the x. Well, a is our initial value, y-intercept. So we have 2 times 3 to the power x. Asymptote is going to be y equals 0, the function value that the function approaches but does never reach. The domain for all exponentials is negative infinity to infinity, all real numbers. And then the range is everything greater than 0. So 0 to infinity. Okay, example 6. The function f of x models the number of people who have seen a meme after x minutes. Each person who has seen the meme shares it with 5 more people every minute. 2 people originally created and saw the meme. Write an exponential equation that models the situation. So if we were to model this using f of x, we know that the original value, the initial value, is going to be 2 because 2 people originally created the meme. Now, every time that they share it, 5 more people see it. Therefore, it's going to be the number of people viewing the meme is going to be multiplied by 5 for every time someone shares it. So therefore, the growth factor is going to be 5. So this can be modeled as 2 times 5 to the power x. All right, so let's take a look at example 7. The following graphs show the population growth for two species, species X and species Y. On the y-axis, we see the population, whereas on the x-axis, we see the time in years. Part A, find the growth factor for each of the two species. So looking at species X, the graph on the left, I could construct a table of values by looking at each of these 2 points, 115 and say 245. So we have X comma Y, we'd have 115 and 245. Remember, the growth factor, or the constant ratio, is as we move between successive x's, as we increase by 1, what's happening to y? Well, we're multiplying these y values by 3. Therefore, the constant ratio for species x is 3. For species y, again, we can construct a table of values using these 2 points. So table of values, here we have 150 and 100. The growth factor here is times 2. So our constant ratio is 2. What is the y-intercept for species X, and what does that tell you about the population? Well, if we look at species X, the y-intercept is 0.5. And what does that tell us? That tells us that the population of species X was 5 at the start, or at 0 years. Okay? So we can write an equation now that we have the initial value and the growth factor. For species X, species Y, part C, we want to find the equation that models species Y. So we need the y-intercept for Y. Well, we know that the y-intercept is 0.25. So then the equation that models species Y, the population, is the initial value, 25, times the growth factor, 2, to the x. Okay? Part D, use the model from part C to determine what the population of species Y will be after 5 days. So here we have population of species Y is going to be Y equals 25 times 2 to the x, which remember is the amount of time in years. Because we want 5, this should say years, we can go ahead and evaluate. So we have 25 times 2 to the 5th. Well, 2 to the 5th is 2 times 2 times 2 times 2 times 2, which is 32. And if we were to multiply 25 times 32, we would get 800. So then the population is 800. Do we have units on that? Nope, just 800. All right, so let's go ahead and summarize. A linear function represents a constant rate of change. If we were to look at the graph, this would be a straight line, just a linear function line. This rate of change is called the slope. So how is the function changing as we increase or decrease x? It's increasing by an additive rate of change that we call the slope. One general form of a linear equation, y equals mx plus b, slope-intercept form, gives us the slope, which is m, and the y-intercept, which is b. The shape of the linear function is a line, which is just like a straight line. Okay, for an exponential function, we get a curved line. The general form is a times b to the x and gives a constant ratio or a growth or decay factor, which is b, and the y-intercept is the initial value, a. All right. So these have been our notes on 6.2 exponential functions. We're going to get a lot of practice on this in class, so we'll see you tomorrow. Have a great day, everybody. Goodbye.